The idea of, probability of, what's the easiest thing to do is flip a coin, and I want to go heads, 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 in that sequence. I'm going to flip a coin 3 times, which means I forgot to bring a coin. If we got a coin, I promise I'll get it back.
I do. Oh no.
No one has a coin?
$1.
I got $1.
I got $1.
That's your dollar.
Gotta be bigger than that.
Thank you. So, just to show that we are not cheating, because we would never do that, this is a coin from 1985. Do you agree?
No.
And that's the tails. That's the heads. Shut up. So, when we flip a coin, is each flip independent of the flip prior to it? So what happens here is that coin flipping is independent each time. So we know that the probability of getting a heads is how much? 1/2. Now, if I'm looking at it, if I'm going to flip a coin 3 times and I want to go heads, 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 what's the probability of getting heads on the first flip? 1/2. Okay. What's the probability then I flip the coin, woohoo, I got heads. So I got heads, woo, I win. And I flip it again. The fact that I just got heads on there, it didn't matter, but I got it again. So the probability of getting heads again was 1/2. And lastly, completely independent of the other two, tails, I lose. Womp, 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 womp. But they still had a probability of 1/2. What happens here is that since each flip is an independent draw, if you will, you multiply them. You multiply those things through. So these are what we call probability. This is the probability of an independent event. What's that? Did I spell that wrong?
You spelled independent wrong.
It's all E's, isn't it?
It's, yeah, there's no A.
Probability of independent. Oh, independent, there's a dent.
There you go.
Okay.
I didn't think of that now.
Sometimes I'm proud of myself. And
That was weird.
that was not good.
I thought that was weird.
That was like, you were like on top of it.
In the pen, there's a dent.
He was on top of that too, like he didn't even like pause.
He didn't even like plan that 3 days in advance.
He didn't practice that one in front of the mirror in the morning.
Unless he did, and he knew that he was going to spell independent wrong, and he knew that we were going to correct it.
He planned this
You
whole
know,
thing.
honestly, I show Connor and Ryan all of my lessons the night before to get the approval or disapproval of a 8 and a 5-year-old. I figure if an 8 and a 5-year-old laugh at anything, you guys will be fine.
Wait, you really do that? You like sit them down for a whole 40 minutes and start the lesson?
No, we don't do the whole thing. We'll just sit down and go through a couple of the pointers.
And the jokes.
Really? Your kids are probably going to be really good at math.
So then you spelled independent wrong. You came up with that joke last time.
No, that one just happened. But talking about coin flips, we talked about though. Because there's 2 sides to a coin. I'm making all that up.
Oh,
Are you kidding
I
me?
thought
My
you were
children look at me
serious.
going, "What are you talking about? I don't care."
I thought that you were serious. I was like,
We-
please.
We're gonna be geniuses. Do they laugh at your jokes?
Sometimes. If there's poop in it, yes. Boys, this tall poop is funny. It's funny.
It was funny because he did have accidents.
It's like angle side side. You are playing a game that involves spinning the money wheel shown. otherwise known as the Wheel of Fortune.
Do you remember when we were playing that?
Bankrupt? Is that actually
It
a
was like-
side?
Yeah.
There's
There's two of them.
Does it actually spin?
So,
It's the
Wheel of
only one that
Fortune.
actually spins.
We can't use the term Wheel of Fortune because it
Does
is
it actually spin?
copyrighted.
If you put an R next to it.
Of course it spins. Why would I not have something that is the spinning wheel that doesn't spin? Come on now. Have a little bit of faith in me.
But it doesn't show you where you land. Like,
Okay,
does it
you know what?
land?
You know, you just draw an
Like
arrow.
you have to draw like an arrow.
That's horrible. That's.
But it's just gonna end in the
land
same
anywhere.
exact spot.
It doesn't land anywhere.
It always lands in the same spot.
See, look at that.
It's
Oh my
rigged.
gosh.
You rigged it,
Whoa, you won $350.
Murphy. Again.
No, I wonder what you're gonna get this time. $350.
All right, so you're playing the game that involves spinning the money wheel shown. During your turn, you get to spin the wheel twice. What is the probability that you get more than $500 on your first spin, then go bankrupt on your second? So we have to win more than $500. So we have to figure out where can we win more than $500.
5,000.
550, 1,000, 650.
750.
Wow, it's like all the A's. How did that work?
Oh,
Are you kidding me?
are you serious? Why can't we just count the A's?
This is the probability of A.
Are you
and
kidding me? Are you
B.
serious?
Figure that out.
I looked at him, I was
It's
like, all the
like
A's.
all the way around. I didn't.
I was waiting for someone else to notice, so I had to.
I would have never noticed it if he didn't say anything.
Anyway, so how many A's did we have? 1 little, 2 little, 3 little A's, 4 little, 5 little, 6 little A's, 7 little, 8. Now, here's where things get difficult. You have to count how many, for $1 million. What is this? Oops.
Whoa.
What is this called?
3690.
A triangle?
Pizza.
$1 million! You get $1 million. We get you $1 million.
What was it?
What'd you say?
Sector.
Pizza.
Oh yeah,
This is
that's,
geometry.
that's a thing that exists.
It's an extremely
People need to
small
stop
piece of
making up
pizza.
words.
I mean, technically it is a triangle.
Vectors.
You guys want to
No, because the end is curved.
Jeez, guys, thanks.
Man,
You're welcome.
you took out there.
Texas.
Vegas, baby. What? I'm going to Vegas. Feel like Vegas. Feel like
You would go to Vegas and like, you would either win or lose everything.
I present to you, ladies and gentlemen, she guessed correctly. She remembered her geometry. Her check, $1 million.
Now Murphy.
Where's the big check?
Hold the check. Got it.
If anything you guys remember about this class is 2 things. Hopefully the only things you guys remember from this class is, well, trig, and
Bad jokes.
or at least we tried to have a little bit of fun.
Oh no.
So, alright.
Keyword tried.
I mean, he roasted.
Go Captain!
Good luck.
Violent
Yes, ma'am.
If she's walking out, I'm out.
That's great.
Where are you going?
She's walked out.
She's going to state.
He's like laughing.
I'm very excited. I should be a game show host.
You really should.
Oh, geez.
Except for you and your
Yeah.
Math.
Wheel! Alright, so let's count these.
Each time someone spins
Make
that.
sure there's not like
Alright,
a
ready?
special-
Let's count. 1 little, 2 little, 3 little sectors, 4 little, 5 little, 6 little sectors, 7 little, 8 little, 9 little sectors, 10. A lot more to go. 11 little, 12 little, 13 more sectors, 14,
You gotta go fast.
15, 16 little sectors, 17, 18, 19 little sectors, 20, 21, 22, 23, 24 sectors.
Oh, you.
thought I got lost there for a second. So it's 8 out of 24 is the first one.
I tried to mess.
How many spots can you go bankrupt?
2.
So it's 112.
Multiply that through. Obviously, you can simplify stuff right away. You could go 1/3, 1/12. You get 1 out of 36.
Wait, you multiply?
They're independent. Each one of those spins, we're independent of each other, or we're independent. So when you talk about independent probabilities, you multiply them together. Excuse me. All right. Congratulations again.
What is that?
It didn't
No,
work.
no, you go back.
Oh, I want to see it though.
Can we just like
Wait,
look
what
at
was
it
the
for a
answer?
minute?
I don't know, 136. During the baseball season of 1997, the Florida Marlins won 5 out of 7 home games and 3 out of 7 away games during the San Francisco Giants. During the 1997 National League Division Series with the Giants, the Marlins played the first 2 games at home and the 3rd game away. The Marlins won all 3 games. Estimate the probability of this occurring. Can you put that in English? Okay. So the Marlins won 5 out of 7 home games and 3 out of 7. 3 out of 7 away against the Giants. And that means that their, I'll say that their experimental probability of winning, or their actual probabilities of winning at home against the Giants were 5 out of 7. Their winning probability away against the Giants was 3 out of 7. You can't just say that they would win 8 out of 7 times by adding those 2 together, because obviously you can't win more than you can play, so you don't add fractions. So what happens here is that you're looking at a compounded independent probability where you have to piece together, you want to win, probability of winning a game at home, and away, to win 3 in a row. Very good. The actual probability then of that occurring, as you start putting it together, is the probability of winning that first game at home using what their regular season record was, would be 5 out of 7. Winning the second game is totally independent of winning the first game because it's just another game. You also have 5 out of 7.
So if it was said like, it was like they won the first game, lost the second home game, and then won the away game, would it be like 5 over 7 and then like 2 over 7?
Very good.
And then, okay.
Very good, very good. Yeah, and you know what you just used?
The thing that I asked, properties of complements?
Exactly. And you put all that together. 75 over
343.
Very good. So the actual probability of all of this occurring to win like that was 75 out of 343. What's the decimal of that?
219.
So we'll say 0.22.
So it's 22% chance that was going to happen?
Yeah, and if you look at it, 5 out of 7, that's better than half, isn't it? So you start really thinking about win probabilities. Now, remember, this book was written back in 05, 04, somewhere in that neighborhood. So you're using statistics from late 90s a lot of times. Nowadays, if you're a baseball nerd, you know that there's all these new stats that they have, and they're able to look at all these different win probabilities and things like that. And the statistics of sports now, with computers and algorithms and how they come up with all that, like just the way the Cubs were, how they built their system. If you really go into how Theo Epstein worked with the Red Sox and worked with the Cubs, and how they were able to generate and build all this stuff up via what they call sabermetrics. How the whole Billy Bean thing out of Oakland back in the early 2000s. Same idea. They're taking statistical information and analyzing the data to see what works best for teams. And that's how most teams are run nowadays. It's all stats. Everything is built via math. So, if you like stats, if you like the idea of working with numbers to help benefit anything, whether it's business, sports, whatnot. Statistics really do run just about everything. Pricing, optioning, what things go to where, financial planning, it's all built off of trend analysis via statistics. Stats is one of the coolest things you can do. I mean, remember, 80% of stats are made up on the spot, they're half right.
So that means 40 more. Wait, no, never mind.
Yes, sir.
Never mind.
So, but think about this. Most baseball teams would have different stats because the players will switch around, and that affects it.
But here's the thing, you can normalize it. You can normalize, like WAR, wins over replacement. You can normalize a WAR stat versus a guy, instead of just running batting average. Batting averages nowadays are kind of passé. Wins, losses, really doesn't matter. It's more about the quality start of the pitcher versus, what it is. The save doesn't matter. Were they able to stop? Because you can have is there a middle closer? Is there a guy like what you've seen nowadays in baseball? You got a guy coming in the sixth inning and stops everything. And then you reset. So there's so much stuff you can look at data-wise. The spray charts, you start looking at why they play shifts on certain people. Certain people are shifted over, and just because that's where the tendencies, things like that occur. Football, same deal. Football, they run analysis of what plays run at certain sequencing. People are always analyzing data, going back, watching. That's why you watch film. Oh, math. Dependent. Dependent is different than independent because each individual draw depends on what happened preceding it. And this is kind of what you were asking about yesterday about how when you're dealing with cards, does it matter what happened prior to? I think you were asking that? I don't remember.
I don't know, probably.
Might have been me.
But it was somewhere that...
About, like, if you roll a 1 and a 2 and a 3,
Dice rolling is always independent because you have to pick up the dice and roll it. It didn't matter what happened prior to it. Whereas cards.
Oh yeah, that's what I was saying, because I was saying like when they were playing blackjack, they saw all the cards that so then that means that the other card couldn't be drawn. Like
Correct.
that same card couldn't be drawn again.
Because of dependency. And that's where you have to read carefully. And you were thinking that. You have to start reading carefully as far as what is happening within the deck of cards. For example, if two things are dependent, we say that probability of A and B occurring is the probability of A times the probability of B such that A has occurred. It sounds weird how it's written, but when you do a problem with it, it makes sense.
Well, then let's do a problem.
I'm not going to. Here's the one I had in here. So think of this one. What's the probability of, well, I have it on the next slide. Can I go to the next one? Instead of writing it out. Randomly select two cards from a deck of 52. What's the probability the first card is not a face card and the second card is a face card? Two different ways. If you replace the first card before selecting the second, or you do not replace the first card. So, probability of not face and then get a face. Now I'll do this. What this is called with replacement. And we'll do one without replacement. With replacement, isn't each independent draw, or isn't each pick of a card independent of each other?
Yeah, because a face card isn't a face card.
Well, and not just that, but how many cards are still in the deck? A lot, right? That number is 52. So if you're putting the card back in there and you're drawing again, that probability of the next thing occurring, it didn't change. You don't have any different number of cards there. The whole idea of with replacement, without replacement shows dependence, depending on this one happening. Or sometimes it'll say, What's the probability of getting a 3, then a 2, then, getting a straight in an order, something along those lines. And this is where we spend a little bit more time on this stuff, especially tomorrow. I've got a couple of worksheets that have a lot of card stuff on it. And we'll talk about these things. Okay? So looking at a replacement, not a face card, but a face card. How many cards are face cards? 12, which means how many are not? 40. So not a face card is 40 out of 52. Again, all we did there was just use the complement rule by knowing that there's 12 face cards. Backed it out of the 52 gives me 40 no face cards. Or you could do that as well if you want. Now the probability of getting not a face card and then getting a face card is that. Now it changes then. What do you get for a decimal here? A big number? Well, it's a decimal, so it's not as big as you may think. It might just be fractional of that large number.
It's 0.1775.
0.1775?
Well, I mean, it keeps going.
Yeah, it's close-ish. Now, without replacement, the first card I draw is going to be no face card. Well, how many non-face cards do we have? 40. I don't put that one card back in the deck. How many cards in the deck now?
51.
Of those, how many are face cards?
Wait, but what if you drew a face card first?
We're saying what's the probability that we don't get it and
Okay.
then we get a face card after it. And it goes down by 1 because there is one less card. Lottery. Each one of those is, they're independent draw, but what's happening since they're not being replaced, it's conditional. So, what do you get for this one then? Going 18, oh.
Well, just
And it doesn't seem like it's that big of a difference, but as you start really, if you really get into counting cards and start figuring out what's available, like you were saying with the blackjack stuff, you really start thinking, okay, well, that's been out, that's been out, that's been out, but what else is there?
Well, obviously that makes sense that it was a greater chance because it's saying like if you chose a not face card first, then that's just a little bit more probability that you will choose a face card the second time. It's not first.
Yes. But remember though, it's not that this is a greater probability that you're gonna, oh, you're saying because, all right, but you had to you had to leave that card out. It's going to be a greater probability because there's one less card. I think that's what you meant.
Yeah, because
Okay.
there's one less not face card when you're choosing a face when you are trying to choose a face card.
Correct.
So then when there's one less face card, then there's greater probability that you won't choose. You know what I'm saying?
I kind of see where you're at. I'm going to stop here because it gets nuttier, and I don't want to do all that in one day. So let's do this.
Alright, so we're not turning this in, so I don't have to do this on like a separate page. I can do it on my notes.
Yeah, that's fine. Because then we'll start talking about. Then I'll leave you with that one. Did I put 24 in there? Okay. We'll get to the lawnmowers, free throws, all that other stuff. We'll do that tomorrow with the actual independent dependent stuff. We'll talk about unions, intersections, all that kind of junk tomorrow. Yeah, we'll leave it at that for now. Here.